Well, thank you, Robert. Thanks for the kind words. Welcome, everyone, and excited to be here. I would like to give you an overview of Azure Quantum as a platform to develop quantum algorithms and show you some examples for the kind of research that's enabled by the platform. Let me just start with something we all are, of course, familiar with and know. Kind of the quantum computer has the big promise to outperform classical computing. And that being said, it's sort of a priori unclear where these crossover points actually are. It's very problem dependent, where you can actually get better using a quantum computer, where you have this sort of quantum advantage. And we're looking at different problems and at different ways to measure the input size. I'm going to give you a few examples in a moment, but it's sort of a really tough problem to get crisp and really precise on these crossover points. And that's in a sense of like, that's the core of a lot of research, right? One can approach that question asymptotically and study it basically mathematically or analytically. It is kind of, from the programmatic point of view, very interesting to implement the algorithms then to further get confidence on correctness when you run them on small simulators, or like in special cases, you can actually simulate at scale if you know more about the structure of your circuit. But then you get more confidence about the actual crossover points. So that's sort of the driver of a lot of research we do at Microsoft, and we know that the community, many people who care about really understanding what is that problem size, and related questions such as how big of a quantum computer do we actually need to build to get to that crossover point. So I want to give you a bit of more flavor, also what Azure Quantum is and what you can do there today. So just on the problem, the kinds of problems, of course, most of you are familiar with the kind of how the field really started. That was the factoring algorithm and the discrete logger algorithm by Peter Shor. How that plays out is, so you could actually study the classical scaling, and the many algorithms on the classical side, one can extrapolate how they scale. Quantumly, one can do the same. One has to make assumptions about the clock rate of these large-scale quantum computers that would actually get us there. But here's basically, in a nutshell, a picture that summarizes this scenario. Classically, the methods are, they are sub-exponential, but they scale kind of in a way that for a bit size of 2048, which is the industry standard right now for RSA, it would literally take billions of years to break it on classical machines. Quantumly, using the period finding algorithm, if you make an assumption that the machine is clocked at a megahertz per basic instruction, let's say being like Clifford and T instructions, you could arguably bring it down to a day of compute time on a quantum computer. And sort of the different opinions about this, but many people would agree that kind of if we have a cutoff of a day, that's still doable on a quantum machine. If it would run for 1,000 years on a quantum computer, those problems might not be interesting. So that kind of gives a certain pivot towards problems where there is a big speed up, like an exponential speed up over the best known classical methods. So that kind of is one example that can be studied with tools and languages. On our platform, we've done quite a bit of research on the factoring side. Also on the D-log side, we implemented the so-called oracles. Those are the classical pieces that implement the group operations. We implemented those in Q# and analyzed them using the tools for factoring as well for D-log for various curves. Another example that's maybe closer to home and that has more business value is chemistry. So it's very active in the community, in the entire field, active research on simulations. Many methods have been investigated. We had we were slowly chipping away at the problem of understanding quantum simulation for chemistry applications at Microsoft, starting out with some algorithms that had polynomial scaling, but the polynomial was a pretty high degree. I think it was something like n to the 11 or so. And then even on a quantum computer, you do get a speed up to get the kind of ground state energies, but it is still running on a for a very, very long time. And so by improving these methods, first it started out with Trotter methods, then there were various trade-offs that were discovered and improvements. And eventually the kind of new methods came along, such as qubitization, LCU methods. They were able, using these methods, the field was able to get to runtimes that are now arguably under a year. So there's still a very active area of research. And sort of you use a quantum computer there as a co-processor to get very accurate estimates of energies. And then classically, you of course also have a loop to modify your chemistry problem. So that's kind of, it's a scenario where you use a quantum computer as a co-processor, but at the same time you drive the classical compute in a big cycle. And it's probably not going to be just one energy evaluation ever to solve a really meaningful chemistry problem. You probably need a lot of calls to the quantum coprocessor. So I want to pivot a little bit here and say a little bit about the resources also from the physical level. So it's important to understand that to build a machine that's capable of tackling these large-scale problems, we must have a fault-tolerant quantum computer. And this figure here in a nutshell summarizes the importance and gives also an idea of the scaling and where we need to be in terms of a regime. So here you see on the x-axis is the physical error rate that the underlying hardware exposes. And on the y-axis, you have the number of physical qubits. To get to a regime where you can have very low error rates at the logical level, let's say 10 to the minus 12, 10 to the minus 15, those are the regimes you need to get into to do large scale chemistry and crypto applications and potentially other quantum applications. And say, let's say you want to get there and you want to have a number of logical qubits that's maybe in the hundreds, let's pick 100. Then you can plot what the curve looks like, the trade-off curve, physical error rate versus number of qubits, physical qubits that you need to have a fault-tolerant machine. And you can see, of course, here it's very striking. There is this so-called threshold for fault-tolerant quantum computing, meaning if you are above the threshold, if your error rate is too high, you can actually never implement a large-scale quantum computer. If you are away from the threshold, you got a decent error rate, maybe 10 to the minus 3 or lower. The scaling is quite nice with the error rate. If you're too close to the threshold, you go into this singularity. You can still build a fault-tolerant machine, but it requires a lot of resources, meaning you have to go to pretty high distances of the underlying codes, which then uses up a lot of resource. And just to manage the expectations where the field is at, we are kind of the NISQ machines. It's very exciting that these machines exist, and one can access them and play with them. But the NISQ machines today are not at that regime yet. So they are kind of, the error rates are too high, the number of qubits are too low. We believe we have to get at the physical rate to error rates that are over here to really make a scalable machine. That just comes from that's to illustrate the physical aspect of building a quantum computer. And it is sort of, that's what we believe at Microsoft, that kind of to make a meaningful progress for business relevant applications, you need at least 1 million physical qubits. Just to kind of get started with chemistry and crypto, you need to have that many. That gives you then the number of logical qubits you need to tackle those applications. For material sciences, it's even worse because the systems are very large. We're talking about systems having maybe 10 to the 9 atoms or so. To map them to a quantum machine and then investigate them, we need even more qubits. To start with basic science and understand physics, localization, phase transitions, and all these things, it starts earlier. We can work with smaller systems, but also there to really go beyond what can be done on a classical machine and innovate scientifically. It's probably tens of thousands of qubits. And in this plot here, we are, of course, as you all know, on the sort of on the leftmost pixel in this chart, right? So the ion traps and superconducting systems are all the way over here. At Microsoft, we work hard to build a so-called topological qubit. We're not quite there yet, but we make good progress towards it. It's still all on this very leftmost part of this chart. And so I want to pivot now towards talking a little bit about the about this understanding this even better, this issue of nailing down the trade-offs and understanding the precise resources you need to tackle a given problem. So we call it the resource estimation. Of course, the entire field calls it resource estimation. It's an active field of really quantifying the resources needed to implement a given algorithm. Ideally the physical resources, but on the way to physical, we want to have first a good handle on the logical resources, say Clifford and T gates, the depth of circuits, the number of qubits. But then as another step, we'd really like to get to the physical level. And that's why I showed the previous plots about the physical error rates. For that, you have to now make assumptions about the underlying physical system, the error rates, the gate times, and so on. And then you go in a multi-stage process where you first investigate the algorithm on a logical level that tells you something about the workload. Then you figure out how much error correction you actually need for your underlying physical system. And then you go back and you translate that into how big the factories need to be to distill T states and compose everything together. That gives you then eventually physical estimates such as the wall time that the machine will need to execute a given workload. You can get the number of physical qubits. You can also get estimates of the area of your chip if you know kind of the structure size of a single physical qubit. It gives you that information. And when you get to the physical level, it's of course very important to take into account the connectivity of the machine and all these geometric constraints that you might have to take into account, that they also influence those estimates. So long story short, we're building resource estimators at Microsoft. The first one along these lines was shipped already in the QDK several years ago. It's called the Tracer, or the resource estimator. That strips out from a given Q-sharp program. It strips out the number of logical gates needed, typically over the Clifford and T gate set, but you have more control. Actually, you can go to a kind of more coarse level of granularity and profile the program and say, like, I want to know how many times this and this subroutine is called, what's the depth of the circuit, and all these things. We partnered up with Goldman. The team Goldman Sachs has proposed a quantum algorithm for derivative pricing. And that is an algorithm they implemented then in Q-sharp and used these tools to get precise resource estimates at the logical level. But I'm really excited about this very recent development. These are physical level resource estimators that go the next step after the logical level. This is something we're actively working on. It's currently in private preview, which gives you once you make these assumptions about the physical system, it's all programmatic. They're all can be specified and modified, and you can play with the parameters. But then at the end of the day, you get estimates of the physical execution times. Now I want to just talk a little bit about the overall way we think about folks will develop quantum algorithms. And there's a lot going on that slide, so let me unpack it a little bit for you. So a quantum software developer typically proceeds in a way where they think about the algorithm, and then they pick the right language to express it. There's a whole bunch of quantum programming languages out there. You probably, many of you are familiar with Qiskit, which is developed by an alliance led by IBM. It's a fantastic language to program near-term devices. Cirq, very similarly by Google. Q-sharp can also be used to program near-term devices. My personal belief is that it's really strong at high-level programming and going to scales that are really large and still be able to write the programs and analyze them. But there's this whole spectrum of programming languages that one can choose from. Then, of course, there are libraries. That's a very important aspect. Like, languages are great, but they only get really great by having libraries for all different domains that you work in. You need, as a quantum programmer, you also need to cover your classical compute. There's pre-processing that's needed, there's post-processing that's needed. But that's not all. There's an entire field that's now emerging that deals with all these ideas to do processing on the fly, and the different flavors to it. I'm going to say a little bit more about that in a few slides. But they kind of, you need to then figure out what is your classical driver, what's your classical environment. Python is very popular in the scientific computing world. So that is another framework we support. And by the way, we support in Azure, all these languages are fully supported, C#, Qiskit, Circ. They all run in Azure, and they can be mixed and matched with languages such as Python and .NET languages like C#. So that's definitely possible. Then as a next step, once you express your program, you really want to make sure or get at least some sense about the correctness of the program. That's very hard in quantum because we don't have the large scale machines yet. So what one can do is use simulators of all kinds. There are full state simulators. There are some simulators that exploit special structure of the circuits. There are noisy simulators for different gate sets. So all that kind of helps to write unit tests and get some idea about the correctness of the program. And then the next step here is sort of this profiling idea, the idea that maybe the application you work on will actually require so many resources that it can never realistically run on a machine. These are things you can definitely already investigate today, even before a quantum computer is built, using the tools I mentioned on the previous slide. So we have the QDK resource estimator and the cloud resource estimator that goes to the physical level. And then eventually you want to run the stuff on the hardware, on the real world quantum hardware. In Azure, there are different types of hardware available already, and I want to talk a little bit more about that on the next slide. But that in basically in a nutshell is the typical development flow in quantum programming. So specifically on that last point, like what does it look like in Azure with these different languages and different platforms, backends? First of all, what are the languages? What are the backends? So I mentioned already C#, Qiskit, and Circ fully supported and part of the QDK, and they also run in hosted notebooks in the cloud. So I'm going to do a demo in a moment. I hope this works actually with this environment. What could go wrong doing a live demo, but I'm going to show you what that looks like when you run those things in Azure. But before I do that, so real quick, so these are the languages. The backends today are a variety of quantum hardware platforms across different technologies. There's ion trap technologies such as IonQ and Quantinuum. Quantinuum is the former Honeywell processor that they merged with the Cambridge Quantum to form Quantinuum. So those machines are available in Azure. The ARIA system, which is a 23 qubit system, is available through Azure, and the on the IonQ side and on Quantinuum side, I think it's also a system with about 20 qubits. We recently added Rigetti. Rigetti is a superconducting platform that has several SKUs in the cloud. That means several different machines can be targeted. QCI is not in the publicly available yet. It's in private preview. If you're interested, let us know. We can get you into the private preview. It's also a superconducting qubit system. It's interesting that they have a lot of hybrid compute capabilities already today. They kind of built that into their vision, how to build a machine to support hybrid from the get-go. We announced earlier this year that we are adding Pascal, and that's also in private preview. Let us know if you're interested in testing this out. This is a non-gate based quantum computer. So it's a system where you have some control over the couplings, but then globally just have a quench operation you can apply, and then you can let the system evolve. It's great to explore optimization problems with that, with an architecture like this. And there's a lot of excitement around these neutral atom platforms. Eventually, we'll add our own qubits in the cloud, of course. In the meantime, we have these resource estimators and all kinds of simulators. And I'm showing this slide also to give an idea of the complexity. There are many languages here. There are many backends here. So the idea is to go through a to an intermediate representation that abstracts out the concrete nature of the hardware you're trying to target. If we didn't do that, we would end up with a mess like this. We would have to basically write translators from every language to every backend, which of course, if there was infinite resources and infinite kind of value in doing that, one would do it. But it costs a lot of effort to do all these specific targeting for different hardwares. So instead, we're following an approach where we're going from all these languages to a level that abstracts out from the hardware, but it's an intermediate level. We call it QIR. And from QIR, then you can target specific backends, such as the various quantum hardware backends, simulators. And simulators includes stuff that runs on your laptop, stuff that runs in the cloud. It even includes stuff that runs on supercomputers, such as Summit or Perlmutter. So we have built all these interfaces to run the codes end to end. I want to speak a little bit about what this QIR actually is. So to me, that's extremely fascinating and exciting. It requires many people and working together. So there's an alliance. There are many institutions, commercial as well as government labs, and it's very open. So they're part of this. It's a growing alliance, and the idea is to build on existing compiler technologies that already has been established classically and has a lot of ecosystem around it, so that people have already written a lot of compiler passes and optimization passes for that classical underlying language. We chose LLVM as that because that has exactly these features. This is very active. There are many compilers from languages to LLVM, such as C or Rust and many other languages. And there's a lot of active work on LLVM making optimization passes on the entirely classical side. The idea is that QIR expresses not only the quantum pieces, it expresses classical and quantum pieces. And we can then leverage also these existing classical passes, plus new quantum rewrite passes that the community develops. It is, as I mentioned, language and hardware agnostic, which then reduces also the kind of complexity going from that mesh of all combinations to just kind of a number of translators from the languages to the IR and then a number of backends. And it allows also, and I'm going to show some examples there. It really empowers this hybrid workflow paradigm where you have classical and quantum meshed together in one program. And finally, you kind of connect end to end and take full advantage of all these technologies that are there in the back end. And just on that point, hybrid. So that's a very exciting new development in the field that people are now thinking about. How is this nature of my quantum algorithm really? Like, what are the elements, and can I maybe enhance a quantum algorithm by having classical computations that are happening on the side? And when you look closer, this can actually happen in many different flavors. So one flavor is that you literally just have a batch of a program and you send it to a quantum computer. They could even be independent of parameters to be tuned, and you just have a certain number of shots of your experiment. That is your payload. You execute it as a batch. Slightly more interesting is if you have inside your batch, you have some interaction. Maybe you have some kind of dependency that you want to train a model. So some of you might have heard of variational methods. So that those are methods that update a description of your circuit. Your circuit is parameterized. You update it based on an optimization routine, and eventually you hope to get to a really good quantum circuit for your task. But there you already have some form of interaction. It's typically, at least those are the examples I've seen in so-called VQE. You do an experiment, measure, you get results, and then you update your model using an optimizer, and then you do it again. In that sense, it's kind of not very strongly coupled, classical and quantum, but it already kind of raises interesting question of like, what is my latency of my entire network? If that's too slow, then it's actually not possible anymore to do these kind of interactive things. And then it gets interesting, like you can go one level higher and say, maybe I want to be able to do my classical computations while part of my quantum system is still coherent. So that is sort of the sweet spot where the field is right now, and tries to find new applications in this stronger form of hybrid compute, where the quantum state stays coherent and you can still do classical side processing. Of course, the first thing that comes to mind there is error correction, right? You need that form for error correction because you need to be able to do on-the-fly measurements, syndrome measurements, process the syndrome information, and do on-the-fly correction. So that's one very important application for that kind of hybrid compute. But there are others, and I want to show you a very cool example on the next few slides. Going further, once we have logical qubits, we still want to be able to do hybrid compute. And I eventually want to do distributed quantum computing and orchestrate really large scale computations like the one for chemistry I showed before, where there's a big classical innovation loop and the quantum computer is used as a co-processor. Those things will require logical qubits, so they are pretty far out at this point still. But these technologies that enable hybrid compute, they are at the cusp of possible, and they are actually they exist already in private previews. I'm excited that they will be in the hands of many people soon, that will democratize the access to those hybrid compute capabilities. And to give an example, so there's a recent paper we wrote with QCI folks on a specific application that uses hybrid capabilities. You can think of it as sort of a blend between VQE methods and QPE methods. So VQE methods are really strong because they're very powerful, because they use only very shallow circuits, so they're perfect for NIST devices. But unfortunately, they're limited in certain ways. In particular, they're limited by the fact that you need like 1/epsilon² many experiments asymptotically if you want to get accuracy epsilon. So that's a lot of experiments to get down to, say, chemical accuracy if you're working on a chemistry problems. And if you have a noisy system, that's sometimes really daunting. QPE, on the other hand, requires very large circuits, right? You're doing phase estimation that requires you to do controlled unitary square, and so on. But they have other advantages, and notably they're only limited by the Heisenberg limit. So you have like 1/epsilon scaling compared to the 1/epsilon² scaling for VQE. So one of the ideas in hybrid is to combine the best of both worlds and to integrate the approaches. And they have approaches that actually do some on-the-fly processing, and that way cut down on the depth of the circuit. It's possible. There was a paper, a recent paper by the previous speaker, Nathan Weeb and Cassandra Grenade here from Microsoft, where they showed, they came up with a pretty cool model that where you train a circuit, essentially. It's described by the mean and the variance of what you think the eigenvalue is, and then you update that in a classical subroutine. So first you do a quantum subroutine, you measure something, you update your model, and then you have to check whether you're done. If not, you keep going, and this happens while the system is still alive. That single qubit that you have, or the kind of the system you have that you operate on, stays alive while you do these classical iterations and the classical updates of the model. And this we have run on the on hardware, on the QCI hardware. Here it was an operator, it was just a single C rotation with an eigenvalue of 0.5. But the point was to prove the concept that it's possible to do phase estimation on the system and get signal that shows that we actually detected the correct eigenvalue. And so this method is called random walk phase estimation. It ran here on that hardware. It did that update that we showed on the previous slide on the fly, using floating point operations and whatnot that was needed to do the modeling. pretty cool. I'm very excited about this kind of work, and I hope to see more of that hybrid work in the future. I want to show also another kind of thing that I'm excited about, but also that I think is pretty useful for researchers. That's a sparse simulator. So the idea is that you want to simulate a wave function as it goes through a quantum computation. Let's assume it's noise-free, so it's literally you apply gates, T gates, to the wave function. But let's say you know for some reason that your state vector during the entire simulation is sparse. So you might wonder, like, does that ever occur? Like, if I apply Hadamard to everywhere, it's automatically non-sparse. What is he even talking about? But it's actually the case that in many applications, the vector is very sparse. That could be, for instance, because of physics reasons or chemistry reasons. There can be particle conservation. There can be all kinds of symmetry law rules that force the wave function to be in a sector. That means there's a lot of zeros and your wave function lives in a tiny subspace or Hilbert space. Another common scenario is in crypto contexts. Folks have switched from modular arithmetic. So you do, like when you do factoring or D-log, you typically work modulo a number. It's either a composite number in case of factoring, or it's a prime number in case of D-log. So you have a modulo operation that you need to do reversibly, and there's methods known how to do the modular arithmetic reversibly, but it turned out it's actually better from the research standpoint to not do the reduction, but to work with states that bake in the modulo operation. There's the so-called coset state approach. Craig Gidney from Google pioneered that to use it in crypto applications and in cost estimates for factoring. It really cuts down the cost. Long story short, that you also get extremely sparse states when you go to these coset encodings, because you have now in like a number x, it gets encoded as x plus multiples of your modulus, x plus n, x plus 2n, and so on. It's very sparse. And as you go through your computation and you track each step, it stays very sparse. So here you already have then two examples where the states are sparse. The idea is then to, instead of work with a long vector of like n qubits 2 to the n, you don't want to track 2 to the n amplitudes. And the idea is to compress it down using a hash map. To every computer scientist would immediately say, yes, we should do that. It requires a little bit of work to really make this correct, so that you can now apply gates and they will be applied only to this hashed representation. But this idea has allowed to break previous records. So if you did not assume any structure in the circuit and you want to do full state simulation, to my knowledge, still the world record is the 0.5 petabyte simulation that Thomas Hainer and Damian Steiger did on the Cori system at Berkeley. That was for 45 qubits. But with these kind of sparsity, like exploiting that, it's possible to do chemistry, like for instance, a 27 qubit system they have benchmarked. It can be simulated now that a full simulation can be done in 15 minutes, whereas previously, like on a full state simulator, the exact same problem took more than a week. And in factoring, it's very striking. So we've done actually way over 100. So there's some examples we did 120 and more in just a few seconds, where just exploiting that structure of the sparsity was exploited, and D-log very much the same thing. So you can go to sizes there of over 100 qubits and simulate them on the machine. That's, besides being able to do that, it's extremely useful for unit tests, as you might imagine. So you can like now write unit tests that cover much bigger instances of problems, and that way you can in some cases find bugs in application that you previously could not find. We have some examples like that. Internally, we found bugs using these sparse simulators that we could not find using the pure state simulators, because they just covered much fewer qubits. And I think this is a good point to switch over to a little demo. What could go wrong? I hope you can still see my screen. Is it still visible?
Yes, we still see the screen.
Okay.
Yes.
Okay. Thank you. I want to show you what Azure actually looks like, what the environment looks like. So in Azure, you have a certain notion of a workspace. It's a quantum workspace where you have your subscription information, you have hosted notebooks, job management panels, you see the providers that are available, and all kinds of other stuff that helps you monitor your subscription. So here, this is, for instance, the so-called SKUs, the machines that are there. You see information about the current queue times, average queue times, availability, and machines you can potentially target. And there will be more added over time here. So you have all these different hardware providers, and their SKUs are here. You also have simulators. There's API validators, there's emulators, and a whole mix of things you can potentially target. Then I find myself these days working a lot with so-called hosted notebooks. So what that means is those are installations of the software that's already in the cloud. So you don't have to install anything yourself. It's kind of a nice thing, because in quantum computing, it's sometimes a little bit painful to install all these complex packages with all the dependencies, and then updating them is sometimes a bit of a pain. So in the hosted notebook, they're already there, they're pre-configured. We have samples that get you started quickly for a lot of languages. Hello World is a very simple one. It's like just a coin flip. You see it here running for different languages such as Q#, Qiskit, and Circ. And then just clicking here will copy it over, and you can run those. And we have more, and there's a growing list of samples. For instance, the large simulation, that is exactly the sparse simulator I just showed in the previous slide. We have a VQE example. I just want to show real quick the Hello World kind, what that looks like on Azure. So it's sort of exactly the same look and feel as a Jupyter notebook. This one runs on Q#. So you can have mix between text and cells. You can execute these cells. They will then show the results also in the same notebook, very much like a Jupyter notebook experience. Here it's Q# based. I'm showing here my subscription. Probably better blank this out later in the video. I don't know. So then I'm importing Q#, and I ask kind of what are the targets that are available that I could target as backends. You see Honeywell, this is the old name. That will be actually deprecated, but we keep it around for now, not to have breaking changes for users who use this old SKU name. But the new SKU names are Quantinuum, so this will eventually go away, the Honeywell name. You see the INQ SKUs, the QPU, the ARIA system, and the simulators. Quantinuum has several systems and simulators. Rigetti has a simulator and several systems. And all these things are now immediately targetable. And what's cool is you write your code once, and you can now target all these backends. You just hook out a different backend for the same code, and it will run. Let's do this for a very simple example. So let's say the INQ provider, select that, and we will build a very simple quantum program that will just do a coin flip. And while we're doing this, this was already executing. Here, this is a so-called magic command. It tells it that's a Q# program. And now you have your Q# code here. It has a bunch of libraries. You allocate a qubit, and then you say, I want to do a Hadamard gate and measure. And then to deploy that, now you can say, I want to pick my backend. So I can say simulator here, and that thing finished very quickly. But I could also say, like, change this out to the QPU backend and run the same thing. So now it will deploy, but it will take a longer time, because the queue times on the quantum hardware, they can be kind of longer. You can select your number of shots here. You can give it a name. Later, you can look in the job management panel, what your jobs are, if they succeeded, or sometimes they fail because the machine could be in maintenance, or like all kinds of issues can happen. Sometimes job fails. That was a Q# example. I also wanted to show a Qiskit example. So this one is the so-called hidden shift problem. It's a little bit about the context of the problem. The idea is to find a correlation between a function and a shifted function. And here we use another resource provider that exposes Qiskit. So now you're able to have any Qiskit code here in these cells. Any libraries that you want, you can import them. All the abilities to plot and so on are also there. So for instance, so this is the quantum program expressed in Qiskit, and you need a bunch of helper functions. And you can do all the good stuff like visualizing the programs. That's all built in Qiskit functions to visualize. And there's all the optimizations also, transpilation and optimize with different levels of optimization all supported. And then eventually you can do sweeps and plot them also in those cells. So that sweeps the instances for that hidden shift, which is a nice problem because it gives a deterministic answer. So you don't have a sampling problem really, but it kind of, you can do all that inside here. And finally, the large simulation, I want to show that real quick. So that is the simulator that simulates the kind of, it scales with the sparsity of the wave function, how much you can do. And here's kind of a very simple example. It's just like a GHZ state, really. Like so, it's very sparse. It's just supported on 0, 0, and 1, 1, 1. First, we do it on the standard simulator. So there's again a magic command here. It's the full state simulator's magic command is called %simulate, and you can see indeed it's supported on 0, 0, and 1, 1, 1 in that case. And then if you go further, you see that we also have a magic command for the sparse simulation, and then we can go again to 6 qubits, works fine, works beautifully, but we can go many more qubits. Of course, that's kind of a silly example, but just to prove the point, like you can go to like 1,000 qubits or so and still simulate the GHZ state on those few. It's very fast. I wanted to show that about Azure. If you're worried about the cost, there's a credit program that preloads these SKUs with $500. So all these backends here, all these machines are already preloaded with $500 of free credits. Most of the simulators are free anyways, but then when you hit the quantum hardware, you can use those $500 to fund that. If you need more, we have credit programs that fund researchers. Send us a research proposal. It will get reviewed internally, but then you get access to much more funding. So $10,000, the typical amount of funding we're giving for those research programs. And in many cases, we gave even more because then to write a full paper, it was just not enough. And some cases 17,000 or 20,000 were enough to gather enough data for a scientific paper. I wanted to show also the local experience. So that was running, all this stuff was running in the cloud. This is running on my local machine. This is a Jupyter notebook running the code. So there's also kind of this entirely local workflow that you can do. You can develop on Visual Studio Code, or in these Jupyter notebooks. And this is a chemistry example. There's a chemistry library where we developed jointly with PNNL Labs here in Washington State in the US. They gave the chemistry expertise, and we hooked it up to the QDK. And kind of, I want to also give a plug that there's a lot of documentation available for all these things, for Azure Quantum, for the Q-Sharp programming language. There's learning modules that teach very didactically. They bring you to the field and teach you quantum computing. There are a lot of code samples besides the ones in the gallery I showed. There's also a lot that run on the local QDK. And there's also an extremely cool thing called the katas. Katas are simple, going from simple exercises to more and more complicated exercises to build up that muscle of understanding how to program a quantum computer. And you basically complete a lot of unit tests along the way, and you make them green, and you feel really good. I can speak from my own experience. It's a very exciting way to learn a new concept, to go through katas and then do it in a programmatic way. We use that also in curricula. And finally, I wanna mention the Azure Quantum Network. We have already these hardware partners. We also have system integrators and software vendors that work with us, that build on our platform. We have customers, folks who actually use the platform for some proofs of concepts, or kind of a longer term strategically who are in an alliance with us. And we have a few university and research partners. And I want to finish off by mentioning that Microsoft made a huge commitment to invest in universities, and in particular universities that have underrepresented minorities, where Microsoft will put millions to do micro funding of individuals over the next years. So that's a very strong commitment to bring further innovators into the ecosystem, and specifically to the quantum ecosystem. Wanted to leave that as kind of the last thought, and as a call to action. If you're interested, it's very easy to get onto Azure Quantum. If you struggle with it, let us know. Here's a pointer to the credit program. I mentioned the $500 and the $10,000 program. And there's various previews currently underway. I mentioned the resource estimator, I mentioned Pascal and other hardware. So also let us know if you're interested in participating in any of those previews. Thank you very much for your attention.